Hello, my name is Giovanni Kalika. I am part of the SAE Green team. My teammates are Matthias Burr, Michael Cece, Daniel Gonzalez, and Anastasia Green. We were tasked with creating a small-scaled UAV. So some rules and objectives of the project. The rules, we needed a 450-watt power limiter, a 36-inch maximum wingspan, take off from a 4 by 8-foot platform that is only 2 feet above the ground, land within 200 foot distance, 1 minute to unload delivery box and payload plates, and use no lead. The objectives were to achieve flight, score the greatest number of points possible, maximize our cargo delivered, minimize empty weight, and maximize our top speed.
Hello, my name is Anastasia Green, and I'll be discussing our configuration and motor selection along with detailed design. Now, when it came to our configuration selection, and after much debate concerning lift, we determined that our best bet would be a delta blended wing configuration, utilizing 3 airfoils. Now, after we're looking at the data from airfoiltools.com and collecting our own data, we're putting 6 airfoils through XFLR5, we determined that the NACA, Epler, and Wortman airfoils shown in this slide will be best for our usage. First for the space, the other 2 for the lift provided. Now, when it comes to the motor configuration analysis, we utilized eCalc to determine what combination of motor and propeller would give us the most thrust for our configuration and the power limitations provided. After this analysis, we determined that the Scorpion A 3017 motor, along with the 10 by 10 APC Sport propeller, would work best for our usage.
Hi, my name is Matthias Burr, and I'll be talking about our CFD analysis, which was done in ANSYS Fluent. The first step in our analysis was to create a solid body model of our UAV. That means it had no internal structure and was made out of one surface. Then we built an enclosure centered on the UAV's geometric center and created the mesh, which was made up of 480,000 elements. We used 7 SOIs to refine the mesh on the UAV's surface. Within the sphere of influence, the element size was 0.02 meters, and for the rest of the enclosure, it varied between 0.07 and 0.15 with a growth rate of 3. For our residuals, convergence was reached very quickly. In all cases, the max iterations was set to 500, and convergence was achieved in around 100 iterations. Here we can see our dynamic pressure contours. The top row is at 15 meters per second, which is approximately our flight speed, and the bottom row at 5 meters per second, closer to our takeoff speed. You can see we have a lot of drag around the rudders and a lot of lift around the edges of the aircraft. Here's our lift versus angle of attack and drag versus angle of attack graphs. Our takeoff angle of attack was based on this data, and we set it at around 19 degrees. The simulation was set up using a standard K-epsilon viscous model and was carried out between 5, 10, and 15 meters per second, and angles of attack of -10 to 25 in increments of 5 degrees. Thank you.
We conducted extensive FEA analysis on this aircraft. So as you can see, we see some stress and deformation results here. This is due to the type of loading we would experience in flight. So we see a lot of blue in the stress and then some deformation along the wingtips. So aircraft will be able to withstand any of the stresses put onto it while in flight. And then here we have some results showing the stress and deformation if you were to just hold the aircraft up by the wingtips only. So we see a lot of stress in the back of the aircraft along our main spars. But overall, the aircraft seems to be much below the yield strength of the balsa wood that we will be using. So this design was ready to be manufactured.
Upon obtaining the results from CFD and FEA analysis, it was determined that balsa was definitely a viable material for this UAV, along with decreasing the empty weight by making most of the bars and ribs an 1/8 inch as opposed to a 1/4 inch thickness as previously designed. And the parts of this design that are unique to this project come in the form of the custom hinges is at the top and the custom front landing gear. Now the custom hinges were made in SolidWorks, so then the UAV could open like a clam to enable speedy unloading time. And the custom front landing gear was made to ensure manufacturability during the manufacturing process, utilizing a smaller front landing gear, a thin metal rod, our chosen servo as shown in this slide, and a custom 3D printed attachment, which is more in the form of UI and can be seen in the front view of the UAV.
Hello, my name is Daniel Gonzalez, and I will be discussing the testing and manufacturing processes underwent for the UAV. The testing began by first looking at each subsystem individually to see how they operate independently from one another. One subsystem that was tested was the electrical system, which consists of the battery, the power limiter, and the arming plug. This was done to determine the voltage that would be delivered throughout the UAV. The other subsystems that were tested were the propulsion and control circuit systems. As you can see, the propulsion system testing was done with a small wooden stand that had the motor and propeller fastened to it. This was placed onto a scale, and once the throttle reached the desired output, the amount of force was recorded. For the servo motors, each of them was tested the same way, by first being connected to one of the channels in the remote controller's receiver and moving the analog sticks to see how the arms on the servo motors reacted. During the design process, the team decided to create multiple airfoil-shaped ribs and have them change along the span of both the wings. However, it was advised that we consider implementing a lattice structure for each airfoil to decrease the weight of the UAV while maintaining enough strength and rigidity in the material. The latticing was then used for each rib while using small spars to connect the ribs to each other. Further on in the assembly process, the UAV started to finally resemble a small-scale aircraft with the main body fully assembled. The structure of the UAV was assigned so that the payload weight could be added by opening the top of the UAV with a hinge mechanism and having a fastener on the back to keep it closed during flight. While wood glue was the main adhesive used to hold the entire structure together, a multi-component epoxy was also used to go over any sections that required additional structural support.
Hello, my name is Michael Ceci, and I'm going to explain our performance metrics. So for our chosen motor of the Scorpion A3017 motor, we ran calculations on eCalc to find the static thrust and dynamic thrust values. From eCalc, it was determined that our static thrust would be about 115.5 ounces, or 7.21 pounds. Our dynamic thrust was calculated around 67.9 ounces, which translates to 4.24 pounds. Next, equations were used from flight mechanics to determine our total distance to takeoff. To ensure we take off within 8 feet, this calculation was done without a tailwind, and it was found around 7.284 feet. Similarly, our estimated landing roll distance was found to ensure we'll be able to land within 200 feet. Using equations from flight mechanics again, we found a landing roll distance of about 22.99 feet. Next, we evaluated our advantages of our design and comparing it to previous results from previous years. Advantages of having a delta wing include a higher lifting capacity than a monoplane or a biplane design. This also means it has a higher internal volume and can fit more within its cargo bay. The blended wing was chosen as it generates a greater surface area for lift. It also decreases the number of sharp corners in the design. A lattice structure was chosen to ensure we'll have a lower empty weight, being more aerodynamic, and to have room for wiring to go in between the ribs. Overall, our scoring analysis predicted an individual score of about 24.33 and a total score of about 72.99. Compared to previous years, this stands within the second and third team that placed overall in last year's competition. Our ground distance versus time plot looks like this, and the equation was given by the velocity and the acceleration. Next, our altitude versus time was taken here, and it appears to be a mostly linear relationship until we get to our altitude of about 150 feet, which is where we set our ceiling. Thank you.